Okay. Okay. So as other join the meeting, we can go through these questions. Okay. So what is the answer of first one? Am I audible to everyone? Am I audible to everyone?
Yes, sir.
Okay. So we will discuss the questions and their answers in first 5 minutes. Okay. So here the answer for first one is D. Okay. Sorry. Answer for first one is A, B, C.
A, B, C.
Right. Mm, just a second. Okay. So here for an isolated system, isolated thermodynamic system, what will happen if we consider this is an isolated thermodynamic system? Okay, there will be insulation at the outer case. Okay, that's why there will be no heat interaction will be there. Okay, so this is the correct one. There will be no work interaction also, because there will be no energy interaction with the surroundings. The isolated system, any isolated system does not interact with surrounding through a mass transfer or through a energy transfer. So obviously there will be no heat transfer, as well as there will be no work transfer also. And as we know, isolated system does not transfer its mass. Okay, mass cannot cross its boundary, so there will be no mass flows across the boundary of the system. Okay, but there may be a chemical reaction takes place within the system. Okay, we cannot mention or cannot decide what will happen in the within the system. Okay, so there may be or may not chemical reaction will takes place within the system. We cannot say that is there any chemical reaction is present or not. Okay, so D is not correct, but the first three, A, B, C, these three statements are correct regarding isolated thermodynamic system. Okay, so answer will be A, B, C. Okay, in the second option, heat and work are
Point function.
point function. No,
Point function.
no, those are path functions. As we discussed earlier, whatever the process takes place from one state to another state, okay, the work or heat transfer is depend on the path. Okay, path of the particular system. Okay, or we can call it as thermodynamic process. So heat and work is depend on thermodynamic process or a path. That's why heat and works are path function. Those are not intensive properties, or those are not extensive property of a system. This is not a point function, because whatever heat interaction or work interaction happen from system to surrounding is depend on the path that system follows. Okay, so that's why heat and work are path functions. Yesterday we see that. Okay, one statement regarding that. After that, third one is select intensive and extensive properties from below list. Here first of all we are going to select intensive properties. Specific enthalpy is an intensive property, right? Then specific volume is an intensive property. Third one is density, also an intensive property. Okay, and also temperature is also an intensive property. So these are four are intensive properties, because why it is enthalpy is an intensive property, because it is specific. What is the formula for specific enthalpy? Specific enthalpy denoted by small h is equal to total enthalpy divided by mass of a system. Okay, that's why it is not dependent on mass, and that's why it is specific enthalpy is an intensive property. For an extensive property, total entropy is an extensive property, and also volume is also extensive property. Okay, because when we increase the mass of the system, then its entropy also increases, its total entropy also goes increases. Okay, as we increase the mass, volume of that particular system will also increase. So that's why total entropy and volume, these are the an extensive properties. Okay, clear? Clear about the answers of these questions? Okay, so we will move on to the next slides. Next point, as in the yesterday lecture we discussed state of a system. What is mean by state? Okay, then equilibrium state of a system. To achieve thermodynamic equilibrium, you must follow these three equilibrium or these three conditions: thermal equilibrium, mechanical equilibrium, and chemical equilibrium. After that, we discuss what is mean by thermodynamic system when a particular system changes its state from state 1 to the state 2. That particular path is called as process. Okay, then we see the what is meant by quasi-static process. It is almost near to the equilibrium process. Okay, after that we discussed what is meant by cycle when the system comes to its original state. Means here we can say that from state 1 to state 2 and back from state 2 to state 1, it is one complete thermodynamic cycle. Okay, so this is called as cycle. Then we see different types of processes, and most of these four processes are very important in the view of thermodynamic analysis. Okay, so you should know their formulas and other things. Then again, those are the different various processes in that free expansion and throttling processes are actual process. Those are irreversible process. Okay, then we are going to see what is mean by reversible cycle and irreversible cycle, or we are going to see that what is mean by reversible process and irreversible process. Okay, so here the initial conditions are restored at the end of the cycle. Okay, the initial conditions are restored at the end of the cycle. That particular cycle is known as reversible cycle. Here in the diagram we can see that when the system is at one state, okay, after as he after some times he goes from state 1 to the state 2. Okay, and it follow path A or process A. After some time, again because of some heat energy interaction or mass interaction, that particular system goes back to its original position. Okay, so what happened at the end of those two processes, process 1 and process B, what happens, system come back to its original position. So this total thermodynamic cycle is known as reversible cycle. Okay, this total thermodynamic cycle is known as reversible cycle because whatever the properties of that particular system or a state of the particular system, it is restored at the end of the cycle. Okay, because the particular system come back to its original position, original state. Okay, after completion of series of processes. Okay, that's why it is called as the reversible cycle. And the properties after the completion of these two processes, the property of the system is exactly same. Okay, it's exactly same to the original conditions. Okay, the exactly word is very important because there will be no any small difference between those properties. Okay, those are exactly same. When those are exactly same, then we can say that the particular cycle is reversible cycle. Okay, and there should be not be any loss of heat due to the friction, radiation, or condension. Okay, so these are three modes of heat transfer. So there will be no loss. Okay, whenever that system comes back to its original position, and whenever it going through those processes, process A and process B, there should be no loss of heat due to the friction, radiation, or conduction because these are irreversible factors. Whenever system consists any friction, we cannot get back that energy. Okay, so there should be not be any loss of heat due to the friction, radiation, and conduction. Okay, so another one concept is what is mean by reversible process. Okay, if we consider, if we plot, there will be PV plot. Okay, we have one system at state 1. Okay, and it follows some path, or it's going through one process and achieve the state 2. Okay, this can be any process. Okay, process we will note it as a process A. Okay, so what is mean by reversible process? Okay, it is very important. Whenever system goes from state 1 to the state 2, what will happen? Its property will changes. Okay, it changes from pressure 1 to the pressure 2, right? So its property of the particular system will changes. Okay, so here when we reverse the process, means direction of the particular process we reverse. 1 second. If we reverse the direction of the process, it's if that particular system follow the exact path. Okay, when we reverse the direction of the process, at that time if that particular system follow the exact path, then we can say that that particular process is रिव्हर्सिबल प्रोसेस. ओके, म्हणजे जेव्हा एखादी सिस्टीम एका स्टेट पासून दुसऱ्या स्टेट पर्यंत जाते आणि पुन्हा जर आपण ती जी प्रोसेस आहे ती रिव्हर्स केली. ओके, रिव्हर्स केल्यानंतर काय होणार आहे? वेन दी प्रोसेस वी कम्प्लिटली रिव्हर्स द प्रोसेस अँड दॅट पर्टिक्युलर सिस्टीम फॉलो द एक्झॅक्ट पाथ, म्हणजे जी ए जी प्रोसेस असते ती पुन्हा एक्झॅक्ट तीच प्रोसेस जेव्हा एखादा सिस्टीम फॉलो करेल, तेव्हा त्या पर्टिक्युलर प्रोसेसला आपण रिव्हर्सिबल प्रोसेस म्हणतो. ओके, अँड इन रिव्हर्सिबल सायकल्स बोथ प्रोसेसेस आर रिव्हर्सिबल. जे काय आपण रिव्हर्सिबल सायकल मध्ये जेवढ्या काही प्रोसेस असणार आहेत त्या सगळ्या प्रोसेस हा या रिव्हर्सिबल प्रोसेस असणार आहेत. ओके, so process A and process B both are reversible processes. Okay, we can change its directions. म्हणजे जेव्हा फर्स्टली आपण ए प्रोसेसच्या ऐवजी आपण समजा बी प्रोसेसची डायरेक्शन घेतली आणि पुन्हा ए ची सुद्धा डायरेक्शन चेंज केली, त्यावेळी जी काही सिस्टीम आपली चेंज होणार आहे, स्टेट चेंज करणार आहे, ती ओरिजिनल ती एक्झॅक्ट पाथ फॉलो करणार आहे. ओके, त्याला रिव्हर्सिबल सायकल म्हणतात. Theoretically, all the cycles are reversible cycles. We consider during thermodynamic analysis, all the cycles are reversible cycle for simple calculations. Okay, because there are some assumptions we can assume for the reversible cycles, and it is very simple to analyze those reversible cycles. Okay, that's why in the any thermodynamic cycle or any thermodynamic process like isothermal process and other, we consider those processes are reversible processes. Okay, so in heat pump, which is operate on reversible cycle, as well as refrigerators, which are we going to see in theoretical manners, those all are work on reversible cycles. Okay, so all constant volume process, all constant pressure process, all constant temperature process, or all constant adiabatic and polytropic process, those are all processes are reversible processes. Okay, why we use reversible process? Okay, most important question, why we use reversible processes or reversible cycles? Because it is very easy, or it is easy or simple to calculate their work interaction or heat interaction. Okay, in this case entropy remain constant. Okay, we will see in next lectures that entropy for the reversible cycle remain constant. That's why it is very easy or simple to analyze those processes which are reversible in nature. Okay, reversible in nature, that's why we consider or assume all the processes, constant volume, constant pressure, constant temperature, are reversible process. So as we know, this is a theoretical process. Okay, it is not actually we can saw it in natural ways. Okay, so there are another type of cycles which are irreversible cycle. Means in it, initial conditions are not restored at the end of a cycle. Here, what happened? Just a second. Okay. Here, an initial condition are not restored at the end of cycle. Here, what happen? Whenever the particular system follow the path A, then after achieving the state 2, it's come back to the original state by using process B. Okay. In reversible cycle, what happen? This particular system follows some path, okay, to the state 3, okay, and does not come back to its original position. It's go anywhere, any other way. Okay. It can go any other way and achieve another state. That cycle or that particular processes are called a irreversible process. Why this is happen or why these irreversible processes or cycles exist? Okay, so whenever any system goes in processes, it causes something loss of heat, okay, due to the friction or due to the radiation or due to the conduction. Because of this loss of heat, because of these reasons, there will be some energy loss takes place during the processes. Okay, when it's follow 1 to 3, there is some energy loss to the atmosphere. Okay, and because of this energy loss, we cannot reverse the direction and achieve the same initial states, because when we reverse the direction of that particular process, we cannot absorb energy from this atmosphere. Okay, okay, that's why it is impossible to achieve reversible cycles in the nature phenomenon. Okay, the causes or reasons behind that are: first one is mechanical or fluid frictions, second one is unrestricted expansion. We cannot restrict the if there will be some free expansion will be there, then it is very difficult to restrict those expansions. Okay, the another one is heat transfer with temperature difference. Whenever there will be heat transfer takes place naturally, we cannot restore the original position of the particular system. Throttling is one of the example of irreversible process, and in natural phenomena or in the nature, most of the processes are irreversible processes. Okay, practically all the processes which are happen in practicals or in happen in natural way, those are irreversible process. We cannot restore the exactly same state. Uh, that system we cannot restore at the exactly same state. Okay, so these reversible processes are theoretical process. Irreversible processes are natural processes, okay, or a practical processes. Okay, generally during for study of any thermodynamic system, we assume all the processes are reversible cycles or reversible processes, because those are simple to analyze. Analyze करण्यासाठी किंवा स्टडीसाठी रिव्हर्सिबल सायकल्स हा सिम्पल्स असतात. दॅट्स वाय वी कन्सिडर आर वी ॲज्युम all the processes which are happening in thermodynamic system are reversible. ओके, नेचरमध्ये काय होतं, थोड्या थोड्या अशा प्रोसेस आहेत की त्या नियर टू रिव्हर्सिबल सायकल्स आहेत किंवा रिव्हर्सिबल प्रोसेसेस आहेत. ओके, दोज आर नॉट एक्झॅक्टली सेम रिव्हर्सिबल. ओके, नियर टू द रिव्हर्सिबल असतं. त्यामुळे आपण काही काही प्रोसेस अज्युम करू शकतो की रिव्हर्सिबल प्रोसेस आहेत. ॲज अ एक्झाम्पल, इफ यू कन्सिडर, let me change color of pointer. Okay, consider there is one cylinder, okay, and there is one piston. Cylinder piston assembly is there. We applied insulation to the outer surface of that cylinder. Okay, also there is insulation on outer surface of the piston. Okay, consider we considering this air which is present in the cylinder as a one system. Okay, in the process A, if we follow that system, it is having state 1. Okay, okay, after that what happen, we compress this air, or we expand this air, means what, we move that piston in up direction. Okay, in up direction. When we remove that, we or expand those gases, as we move that piston in up direction, what happen, volume will increase, and as volume increases, expansion of the gases will take place. Okay, as expansion of the gases take place, what happen, pressure will reduce. So here we can follow this path. Okay, we follow the process A. Here what happen, pressure reduced from P1 to the P2, right? So this follow path A or a process A. After some time, what happen? We compress that gas. Okay, so we move the piston down. As we move the piston down, we follow the process B and achieve the same state which is already earlier present. Okay, after this, what we can say, there will be no heat interaction as all the outer surfaces are insulated. Okay, and here we assume that friction between the piston and the cylinder is neglected, means friction between that particular cylinder and the piston is zero. Okay, if we consider then we can achieve the exact state which is initially is there. Okay, exact state of the gas which is initially present. So this particular cycle we can call it as reversible cycle. Okay, but in a practical view or natural view, if you see that there will be must be some friction between the cylinder wall and piston. Okay, and because of that friction, there will be heat will loss due to that friction. Okay, and we cannot achieve the exact state which is initially is there. Okay, that's why all the natural phenomena or all the practical processes are irreversible process, or some process are there which is very close to the reversible process. Okay, that's why we assume in for the simple calculation, we assume all these cycles are reversible cycles. Okay, this is the difference, because in next whatever the cycles or whatever the process we are going to see in upcoming chapters, those we assume those all processes are reversible processes. Okay, so next terminology, as you study the perfect or ideal gas law. Okay, which is given by the equation PV is equal to MRT. You have already seen that. Okay, it is based on these three laws. Okay, first one is Boyle's law. What it is stated, when we consider temperature is a constant. Okay, the absolute pressure of a given mass of perfect gas is varies universally as its volume. Means if we consider T as a constant, temperature as a constant, then pressure is universally proportional to its volume when we consider T is a constant. Okay, this is given by Boyle's law. Same by the Charles law, we can say that if we put pressure as a constant, then volume of a system is directly proportional to T, right? Because if we considering pressure as a constant. Okay. Similarly, for Gay-Isaac law states that if we consider volume as a constant, then pressure is directly proportional to T. So using these three formulas or three law, we can say that PV is equal to MRT. Okay, here we take M as a proportionality constant. Okay, so by using these three laws, we can say PV, pressure into volume, is equal to mass of a system into R gas constant, characteristic gas constant, R into T. T means temperature. Okay. Here, if we move this V on the right hand side, what will happen? P is equal to M mass upon volume into R into T. Okay. As we know, what is meant by mass upon volume? It is means density, right? So we can write this equation by using this. So here we substitute density rather than mass upon volume. Okay, so it is given as P is equal to density into R into T. Here you can see R is characteristic gas constant. It is vary with respect to gas. If we replace the older gas, then R also varies. Okay, after that, we can also write that PV is equal to small n R bar into T. Okay. What is mean by R bar? R bar is a gas constant. Okay. And it is same for all the gases. Only R is a characteristic gas constant. It is very changes with respect to gas. म्हणजेच प्रत्येक गॅस साठी R ची व्हॅल्यू डिफरंट असणार आहे. जस्ट R जो कॅरेक्टरिस्टिक गॅस कॉन्स्टंट असतो आणि R बार ची व्हॅल्यू जी असते जी गॅस कॉन्स्टंट आहे युनिव्हर्सल गॅस कॉन्स्टंट विच इज सेम फॉर ऑल द गॅसेस. Okay, so if we put R is equal to R bar upon M, this capital M is known as molecular mass. Okay, and again this small n is known for numbers of moles. Okay, if we put these values or these formulas into this equation, okay, so using these ones you can write down P pressure into value is equal to small n, which is numbers of moles, into gas constant, universal gas constant, into temperature of the system. Okay, so these are just as ideal gas laws. Okay, and we consider in the thermodynamic analysis we consider whatever the gas we considering it as ideal gas. Okay, first statement is there that we assuming the air or any gas we are going to consider in that particular system is an ideal gas. Okay, so it must be follow this ideal gas law, which is PV is equal to mRT, or which is equal to P is equal to rho RT, or PV is equal to N R bar T. Okay, you should know the difference between R and R bar. R is a characteristic gas constant which is different for different gases, and R bar is a universal gas constant which is same for all the gases. Okay, so this is the perfect or ideal gas law. Okay, so these are the different equations of the different processes. Okay, you already seen these equations. Okay, so we will see in the next lecture or next part. Okay, these are the four processes which are very important, as already I stated that the first one is isobaric, second one is isochoric, third one is isothermal, and fourth one is adiabatic process. Okay, so these are governing equation of those processes, because in the isobaric process what happen, pressure will remain constant. Okay, as pressure remain constant, so here we know the perfect gas law or ideal gas law is PV is equal to mRT. If we consider there is only 1 kg of mass, then it comes at 1. Okay, so we can neglect m. Then P is equal to remain constant. Then using this equation PV is equal to RT, we can write down T2 upon T1 is equal to V2 upon V1, which is the 2 is for state 2 and 1 stand for state 1. Okay, so whenever there is one process which is isobaric process, isobaric means was pressure remain constant on a PV chart, PV plot, we can plot this process as 1 to 2. Okay, here is a 1 state, here is a 2 state. Okay, when it follow this process, then P remain constant, volume changes from V1 to the V2. Okay, as volume changes, we can write down by using this equation we can write down T2 upon T1 is equal to V2 upon V1, because temperature also changes because of volume change. Okay, so we can, using the ideal gas law, we can write down this equation. Using first law of thermodynamics, we can write down heat interaction in the particular system, which is given by Q is equal to Cp into T2 upon T1, which is also given at dT, difference in temperature. Cp means specific heat at a constant pressure. Okay, and using the formula W is equal to integration of 1 to 2 pdV, or W is equal to normally pdV, PdV, we can find out work done in the particular process. Here what happen? Volume will changes, so work maybe have some value to it. Okay, and it is given by PdV, P into difference between the volume change, volume. Okay, so second one is isochoric process, where the volume remain constant, and using the same ideal gas law we can write down T1 upon T2 is equal to P1 upon P2. Okay, and here heat interaction is equal to Q is equal to Cv into T2 minus T1, which is also given as dt, difference in temperature. Cv means specific heat at constant value. Okay, and work done is 0, as change in the volume is 0, it remains 0, that's why work done is 0 in the isochoric process. In isothermal process, T remain constant, and using the same governing equation we can write down P1 V1 is equal to P2 V2. Okay, and heat interaction is given by P1 V1 into log V2 upon V1, and work interaction is given by P1 V1 log V2 upon V1. In this case, in isothermal process, the heat interaction is equal to the W, or work interaction, means Q is equal to W, because one sec, because here change in internal energy is 0, that's why heat interaction is equal to the work interaction. Similarly, in adiabatic process we have a equation, because it follow this equation, P1 V1 raised to gamma is equal to P2 V2 raised to gamma. Okay, here the value of this gamma is 1.4 for isentropic adiabatic process. Okay, so using the same ideal gas law and this equation, we can write down T2 upon T1 is equal to V1 upon V2 raised to gamma minus 1, and we can also write down this same T2 upon T1 is equal to P2 upon P1 raised to gamma minus 1 upon gamma. Okay, here heat interaction is 0, because there will be this is adiabatic process or isentropic process, where heat interaction is 0, and work interaction is given by this formula. Okay, you already seen those formulas in basic thermodynamics. Okay, in basic mechanical engineering subject. Okay, so we will these are the formulas you should know before we going for next uh, concepts. The another concept is the zeroth law of thermodynamics. Okay, what it is stated that if two bodies are in thermal equilibrium with a third body, we already seen what is meant by thermal equilibrium. Thermal equilibrium means temperature is the same. Okay, so if two bodies are in thermal equilibrium with a third body, then also then they both bodies are also in thermal equilibrium with each other. Means what it is stated here, if we consider this is body 1, okay, this is object 1, this thermometer is object 1. When the thermometer or object 1 is is in thermal equilibrium with body 2 and thermal equilibrium with the body 3, then these two bodies are in thermally equilibrium. Okay, means what? If you consider this is body A, this is body B, and this is body C. If the body A is in thermal equilibrium with body B and body A also in thermal equilibrium with body C, then body B and body C, those both bodies are in thermal equilibrium. म्हणजेच काय, जर टेम्परेचर ए ह्या बॉडीचं ऑब्जेक्टचं टेम्परेचर बीच्या ऑब्जेक्टच्या टेम्परेचरच्या सिमिलर असेल किंवा इक्वल असेल आणि प्लस ए बॉडी ए बॉडीचं टेम्परेचर सुद्धा सी बॉडीच्या टेम्परेचर एवढंच असेल, तर बी बॉडी आणि सी बॉडीचं टेम्परेचर हे सेम असणार. ओके, म्हणजेच हिअर the temperature of a body is, if it is equal to the body B and temperature of a body is equal to body C, then temperature of body B is equal to body C. Okay, it is a statement of the zeroth law. Okay, if two bodies are in thermal equilibrium with third body, they are also in thermal equilibrium with each other. Okay, and this law is used in thermometers. Whenever we measure the temperature of any body, we actually use this law, this zeroth law of thermodynamics. Okay, so how we uses that particular law, we will see in next lecture. Okay, this is the application. Using these formulas and this interpretation, we can know how we use zeroth law for calculation of or measuring the temperature. Okay, then in next lecture we are going to see first law of thermodynamics, second law of thermodynamics. Okay, and after that the applications of second law, application of first law, and after that we are going to cover some numericals based on second law of thermodynamics. Okay, so if you have any query, you can put it in chat box. We have to move very fast, okay, because we are in introduction only. आपण ऍक्च्युली स्टार्ट केलेलं नाही युनिट फर्स्ट अजून. ओके, बिकॉज ॲज पर युअर सिलेबस युअर युनिट फर्स्ट स्टार्टिंग फ्रॉम न्यूमरिकल स्टेटमेंट्स ऑन सेकंड लॉ, म्हणजे जे फक्त आपण सेकंड लॉ पर्यंत घेणार आहे तिथपर्यंत फक्त हे इंट्रोडक्शन आहे. कारण की जे तुम्हाला आतापर्यंत शिकवलं आहे ते पूर्णपणे तुम्हाला बेसिक मेकॅनिकल इंजिनिअरिंग सब्जेक्टमध्ये झालेलं आहे. ओके, बेसिक थर्मोडायनॅमिक्स मध्ये हे जे प्रोसेसेसचे डिफरंट जे काही इक्वेशन्स आलेले आहेत, ओके, याचं प्रत्येकाचं एक्सप्लेनेशनसाठी मी एक व्हिडिओ पुट करेन ग्रुपवरती. ओके, तो फक्त बघा, म्हणजे तुम्हाला कळेल की हे कसे आलेले आहेत, क्यू कसा आलेला आहे, डब्ल्यूचं इक्वेशन कसं आलेलं आहे, फॉर्म्युला कसा आलेला आहे. ओके, हा कसा फॉर्म्युला आलेला आहे T1/T2 हा, या सगळ्याचे व्हिडिओज मी पोस्ट करेन, ते फक्त बघा आणि त्याच्यावर डिपेंड. कारण की ह्या चार ज्या प्रोसेस आहेत त्या खूप इम्पॉर्टंट आहेत. पुढे जेवढ्या काय आपण थर्मोडायनामिक अनालिसिस करणार आहे कोणत्याही सिस्टीमचं, या चार बेसिक प्रोसेसवर डिपेंड असतात. त्यामुळे या चौघांचे तुम्हाला हीट इंटरॅक्शन त्याचे इक्वेशन्स माहीत पाहिजेत, वर्क इंटरॅक्शनचे इक्वेशन्स माहीत पाहिजेत, प्लस त्याचे गव्हर्निंग इक्वेशन्स माहीत पाहिजेत. ओके, सो काही यामध्ये तुम्हाला काही डाऊट्स किंवा क्वेरी असतील तर तुम्ही चॅट बॉक्समध्ये पुटअप करू शकता. You can put up in chat box. We have to move fast because कारण की आतापर्यंत 5 लेक्चर्स आपले कंप्लीट झालेले आहेत, फक्त इंट्रोडक्शन चालू आहे. त्यामुळे हा जो इंट्रोडक्शन भाग आहे तो आपल्याला या लेक्चरचा फास्ट घ्यावा लागला. फक्त तुम्हाला डिफरन्स माहित असून दे, व्हॉट इज मीन बाय रिव्हर्सिबल, इरिव्हर्सिबल सायकल्स, देन व्हॉट इज मीन बाय व्हॉट इज द आयडियल गॅस लॉ, why we use ideal gas law, then what are the different governing equation and heat interaction equation for the different processes, and what is meant by zeroth law, why it is used. Application of zeroth law is to measure temperature. Okay, so if you have any doubts or queries, you can put the doubts in chat box. We remain 5 minutes are remaining. Okay, काही डाऊट्स आहेत का? डाऊट्स असतील तर प्लीज.
No, sir.
हॅलो, डाऊट्स नाहीत का? क्लिअर आहे सगळं तुम्हाला? व्हॉट इज मीन बाय रिव्हर्सिबल इरिव्हर्सिबल सायकल्स? What is mean by zeroth law of thermodynamics? Why it is used to measure? Okay, so I think doubts are clear. जे काही वेगवेगळे प्रोसेसेसचे इक्वेशन्स आहेत, ओके, त्याचे व्हिडिओज मी पुटअप करेन, एक्सप्लेनेशन व्हिडिओज ऑन द ग्रुप. ओके, so it will easy to know how we obtain those equations because these are very important equations. हे तुम्हाला इक्वेशन्स माहिती पाहिजेत, ओके, रिमेंबर व्हायला पाहिजेत, किंवा पर्टिक्युलर प्रोसेसमध्ये वर्क डन किती असतं, हीट इंटरॅक्शन किती असतं. मोस्टली दीज टू प्रोसेसेस in any cycle, any thermodynamic cycle, these two processes are present there. Okay, so ह्या दोन्ही प्रोसेसेसचं गव्हर्निंग इक्वेशन इन द फॉर्म ऑफ टेम्परेचरचा रेशो व्हॅल्यूम मध्ये कन्व्हर्जन करायला, किंवा टेम्परेचरचा इन द फॉर्म ऑफ प्रेशर्स मध्ये, हे सगळं कन्व्हर्जन यायला पाहिजे. प्लस तुम्हाला हीट इंटरॅक्शन पूर्ण त्याचे जे काही इक्वेशन्स माहित पाहिजे. ओके, सो we will see the application of zeroth law in the next lecture. Again, what is the first law of thermodynamics and what is the second law of thermodynamics and its application. After that, we are going to carry out some numericals based on second law. Okay, and after that we are going to see entropy, the most important base concept of thermodynamics, entropy. Okay, सो क्लिअर आहे आजचे जे काही कन्सेप्ट आपण कॅरी केलेले आहेत त्या क्लिअर आहेत का सगळ्यांना? प्लीज टाइप येस नो इन चॅट बॉक्स. ओके, ठीक आहे, ठीक आहे. सो वी विल स्टॉप हियर. वी विल कंक्लूड आवर लेक्चर. ओके, ठीक आहे. So we will end our meeting.